Hello everyone. This is my second video on Chemistry 1, and we're looking at electronic configuration. That is how the electrons are arranged in the atoms. Now, just before we get straight into the electrons, I want to have a quick word about atomic symbols. Here we've got an atomic symbol. Oops, just put that there. X is the name of the element. And Z here represents the atomic number, and A is for the atomic mass. So if, for example, we had a lithium atom, the symbol is Li, it's got 3 protons, so we put a 3 here for the number of protons, and the mass is 7. Now the only way lithium can have a mass of 7 is if it's got 3 protons plus 4 neutrons, makes a total of 7 things in the nucleus, nucleons in the nucleus. Lithium, like this, could also have a positive charge on it, which is quite common. So we will put the charge over here. So there's the 4 things that you might see in a atomic symbol. You might see the symbol for the element, the number of protons down here, the atomic number, the atomic mass over here, and the charge over here. Another one which we could do might be calcium, and so we have 20 protons. Calcium also has 20 neutrons, that makes a total mass of 40, and calcium is often 2 plus charge, so it might look like that. Okay, so that's how you do atomic symbols. You can do one for all of the elements of the periodic table. Now onto our main topic, which is how the electrons are arranged in atoms. That's called the electronic configuration. The electrons in atoms arrange themselves in shells. The maximum number of electrons you can have in the first shell is just 2. So helium, hydrogen, helium. Oops, just get a pen back. Hydrogen, helium. So for hydrogen, the electronic configuration is just 1. And for helium, the electronic configuration is just 2. That means 1 electron in the first shell. That means 2 electrons in the first shell. The second shell has a maximum of 8 electrons. So if we did maybe lithium, the electronic configuration would be 2 in the first shell and just 1 in the second shell. That can go up to 8 if you get further along towards neon. The maximum number of electrons you can have in the third shell is 18, although with the smaller elements you often don't see 18 in the third shell. In an element like fluorine, which has 9 electrons in it, then the electronic configuration of fluorine would be something like 2, 7, because that makes 9. Argon has got 18. So you get argon, 2 in the first shell, maximum of 8 in the second shell, and that leaves another 8 to go. So that would be 8 in the third shell. Speaking of electrons, if you'd like to see a video of an electron, which is something I haven't seen before until just recently, you could check out this YouTube video here. Now, there's a thing called the octet rule, talking about electrons. That says that 8 electrons in the outer shell is particularly stable. Now obviously it doesn't count for things like helium and lithium, because they don't have nowhere close to 8 electrons in the outer shell. But for things like fluorine, for example, fluorine can go to the fluorine ion, negatively charged, so it's got 1 extra electron. So now the outer the electron configuration is 2, 8. And you can see there's 8 there in the outer shell. So this octet rule, which tells us how electrons tend to be, elements tend to have 8 electrons in the outer shell, that is actually quite a useful thing. We're going to come back to that later and have a look at this octet rule. It helps us explain a lot of different things. Now the next little topic is about the subshells. Electrons don't just go into shells, they also have subshells. They go into subshells. And the first subshell, it's like a level, it's like a part of a shell. It's a level, it's a shell within a shell. And the first one is called the S subshell, and that can hold a maximum of 2 electrons. The second subshell is called the P subshell, and it can hold a maximum of 6 electrons. Now the first subshell has a shape which is spherical, so we can just think of it as like a ball, like that. And the P subshell actually has a shape which is more like a dumbbell. Oops, like that, whatever shape that is, that shape there. Alright, so that's the shape of the P subshell. There's that one. There's actually another part of the P subshell looks like this. Same shape and just turned over a little bit. Like that. And there's actually another one as well, which actually goes behind and in front. So you imagine the same shape except going into the page and coming back out of the, or into the screen, out of the screen. It's that sort of shape. So the overall shape of the P subshell is a bit of a complicated shape. It has a shape that looks a bit like that, like a propeller. But we also have to remember there's one coming in and going out of the screen as well. Okay, the third subshell is the D subshell. It can hold a maximum of 10 electrons, and that's got a complicated shape. I can't show you that one. And the fourth subshell is the F subshell. It can hold 14 electrons. That's also got a really complicated shape. Don't worry too much about the shapes. Don't worry too much about how many they can hold, but we do need to know, especially talking about the S and the P subshells, how that works. So remember before I said the electronic configuration of fluorine was 2, 7. Okay, we're going to get a bit more sophisticated now. The first subshell, the first shell only has one subshell. All right, so there's the first shell. It's got a S subshell and it's got 2 electrons in it, just like we had over here. This is the same thing here now, but in a different form. The second shell has got 2 subshells. It's got the S and it's got the P subshell. Okay, so this is the second shell with the S subshell and the second shell with the P subshell. How many can we fit in the S subshell? Well, we're going to fit in 2, so we put 2 more there. That makes 4, but we need to make up to 9. So we can actually fit another 5 in here. Okay, so the electronic configuration of fluorine in the simple format is just 2, 7, but when we get a bit more clever, we have first shell, S subshell 2, 1s2, second shell, S subshell 2, 2s2, and 2p5. And you'll see that in total the second shell has 7, but there's 2 in the S subshell and there's 5 in the P subshell. Let's have a look at neon, which is much the same. Does the same sort of thing, neon. It's got the first shell has got only one subshell, it's got 2 in it. The second shell has got an S subshell, it's also got 2. And the second shell has also got the P subshell, and it's got a total of 6. If you look at the electronic configuration of fluorine, it can fit, look, it's got P5, and the total, of course, the maximum you can have is 6. It could possibly have one more. So a fluorine ion, which has an extra electron, has an electronic configuration of 1s2, 2s2, 2p6, which is exactly the same as neon. So remember I was telling you about the octet rule? Yeah, well, the octet rule tells us that fluorine is going to have this a negative charged fluorine, an ion, has got the same electronic configuration as neon. Now there's another element which has one extra. Okay, so fluorine is 9, neon is 10, and sodium is 11. 11 protons, 11 neutrons. And it has 1s, 2s, 2, whoops, get me out of the way, sorry, up we go, 2p6, 3s1, that's 11 electrons. But the octet rule says it's better if it's only got 8 in the outer shell. So if it happened to be a sodium ion, we'd have to get rid of 1. So just get my eraser and take off the 1, and there we go. So now the sodium ion doesn't have any electrons in the 3s subshell. Once again, look, it's the same. 1s2, 2s2, 2p6. It's the same as the neon electronic configuration. And sodium does actually like to lose 1 electron, and then it ends up with 8 in the outer shell. So once again, the octet rule helps us understand why sodium tends to become a positively charged ion, and helps us understand why fluorine tends to become a negatively charged ion, because they both become the same as neon, and that's got 8 in the outer shell. Lots of elements do the same thing.